Today we're going to look at the last section on this unit on the length of a curve. Some books call this simply arc length. You may or may not recall that we found the lengths of arcs of circles back in geometry. This really doesn't have that much to do with it other than it's the length of a curve as opposed to the length of something that is straight. So if we have a smooth curve, that is a curve with a continuous first derivative, and you're like, oh, a continuous first derivative, right? If we have a graph like that, that's not smooth, right? And at this point, the derivative of whatever this function is isn't going to exist because it's not smooth. Okay, so sometimes they just call it a smooth curve. We can approximate its length by dividing it into n, and where n is some integer, small pieces, then using the distance formula on each segment, notice it's in quotations, of the curve. So like for example, we could break it into a piece from P to Q, and notice that although this is part of a curve, that's almost straight, right? So you could get an approximation by finding the change in x, the change in y, do the Pythagorean theorem, right? You could find this. So the length of PQ would be equal to the square root of delta x squared plus delta y squared. Oh, I've written this right down here, sorry. So that's the length from P to Q. The length of the whole curve then can be estimated by doing that over and over and over again for multiple small pieces. Okay? Now, notice if I were to multiply the numerator and the denominator by delta x squared, so I was to take this and I was to multiply it by delta x squared over delta x squared, but keep the one of the numerator off to the side so that it looks like this. And then I divide my numerator by the delta x squared in the denominator. I get 1 plus delta y sub n squared over delta x sub n squared. And I've factored this out of the square root, so I have delta x sub n. Does that make sense? Colton made a face.
I think it does.
But we're taking this out of the square root, so we don't have the squared anymore. And here we've got, these are the same, and then these are different, so we're left like this. Okay? So if instead of taking a finite number of small pieces, so now we're going to let delta x sub n go to 0. We're going to have infinitesimally small pieces. We end up with the integral from a to b of, notice this is delta y over delta x. The change in y over the change in x is the slope, which is the derivative. So we've got the integral from a to b of the integral of 1, that's the one that's here, plus, that's the plus that's here. This is the slope squared, so it's the derivative squared, times, instead of delta x, we'll call it dx. It's infinitesimally small. It's kind of the way that we think about it. If y equals f of x is equivalent to x equals g of y, that shouldn't be an x, that should be y. Please fix that on yours. Then the length of the curve will be the integral from c to d of 1 plus g prime of y squared dy. And you're like, where did a, b, c, and d come from? Well, you might not have noticed, but I'm going from the point AC to the point BD. So this is the idea of finding the length of a curve. So on page 2, we have these written out. If y is a smooth function of x on AB, we have this integral. And if x is a smooth function of y on CD, we have this one. There are occasions where it's a smooth function of one but not of the other. And I think I have an example of that. I certainly hope that I do. So let's find the length of y equals 4 square root of 2 over 3 times x to the 3/2 minus 1 on the interval from 0 to 1. And you're like, why is that so horrible? It's horrible so that we can do it by hand. This being horrible makes our calculations actually much easier at the end. So ignoring all the other falderall, the 4 square root of 2 over 3 and the minus 1, essentially this is going to look like x to the 3/2. X to the 3/2 is a function that would be the square root of x cubed, right? So it looks like the square root function is just, kind of higher. So that is a smooth curve from 0 to 1. So, okay, I need to find the derivative. So y prime is going to be equal to 4 square root of 2 over 3 times 3/2 x to the 1/2. The 3's happily cancel. The 2 goes into 4 twice. So that's 2 square root of 2 times x to the 1/2. So our arc length is going to be the integral from 0 to 1. They told us where to start and where to finish of the square root of 1 minus, I need to square my y prime. So 2 square root of 2 x to the 1/2 squared dx. So that's the integral from 0 to 1 of the square root of 1 minus, if I square this, that's going to be 8x. And you're like, oh, sweet, I can do that pretty easily. You can do a u substitution if you wish, but since this is a linear, as we talked about, I think we talked about that yesterday or the day before, all I'm going to do is look at, all right, the derivative of that would be -8, so I'm going to multiply by -1/8 times, this is to the 1/2 power, so adding 1 would be the 3/2, so this would be 2/3 of 1 minus 8x to the 3/2 evaluated from 0 to 1. So that's -1/12 of, at 1, oh, sorry, this is supposed to be 1 plus. I was like, what the heck? Not using the right formula. I was thinking, wait a minute, that would mean we were taking the square root of a negative number. This is frequently how I find my mistakes, because you get to something where it's like, well, then that won't work. All right, so substituting in 1, oh, well, that works out really nicely because that's 9 to the 3/2 power. So we take the square root of 9 is 3, cube it, that's 27, minus, at 0, that's going to be 1 to the 3/2, which is 1. So that's going to be -26 over 12, or -13/6. And I'm finding my other mistake now. My other mistake is because I changed this to plus, that needs to be plus. If you get a negative length, alarm bells should go off in your head. And that's what happened. I know you couldn't hear it, but I certainly could. I was like, something's bad wrong here. Sometimes, did you guys ever read the like the Berenstain Bears books when you were little kids? Anyway, it's a family of bears, and the dad is kind of he's very nice and everything, but he's not super smart. And so there's one book, and I don't know what the title is, but he's trying to show his kids how to do things, but he keeps doing them wrong. And he says, and that's how not to ride a bike, right? And so sometimes when I'm teaching, I feel like I'm the dad in the Berenstain Bears books. It's like, this is how not to do this. All right, let's try this one. Find the length of the curve, y equals x to the 1/3 power between x is -8 and x is +8. Okay, so x to the 1/3 looks sort of like this. It does like this, and then comes down here and does like this. And we're going to go from -8 to +8, and we're going to have a problem. Because although mine doesn't really look like it, if we were to zoom in at the origin, it would look like this. Why is that a problem? Yeah, I gave you a hint here. I write those things in the notes so I don't miss them. Yeah, there's a vertical tangent here, which means the derivative is not continuous. So although this is, we would all characterize this as being smooth, it doesn't fit the definition of a smooth curve, which is one that has a continuous derivative. The derivative doesn't exist at 0. You're like, well, then what are we supposed to do? Well, what we can do then is let's rewrite everything as x in terms of y. So this would be x is equal to y cubed. Y cubed is defined everywhere. So we don't have a problem. And if x is, when x is -8, y is -2. When x is 8, y is +2. So we'll take the derivative dx dy, which is 3y squared, and our length will be the integral from -2 to 2 of the square root of 1 plus 9y to the 4th dy. This is not one that you can do by hand, right? I think you can see that, trying to undo the chain rule, you're like, well, I would need something with a y cubed outside of my square root sign, and I don't have anything close to it. So we'll just chuff that into a calculator and see what happens. Wake up. Math 9, -2 to 2. The square root of 1 plus 9 x raised to the 4th with respect to x. So it's approximately 17.261. All right. Wonder why I didn't write calculator on this one. I can't think of any way to do that by hand. I wrote a note on this one to do it with a calculator. So find the length of the curve y equals x squared minus 4 absolute value of x minus x from x is negative 4 to 4. And I'm like, okay, I'm usually pretty good with being able to sketch graphs of things, but this is weird. So I'm going to look at what that actually looks like. Clear out this stuff. So it was x squared minus 4 times the absolute value of x. Oops. Thought I hit it. 4 absolute value of x minus x. I'll do a zoom standard to start with. And then I'm going to change that so that I'm only looking from negative 4 to 4. And you can see where the problem comes. My curve isn't smooth at this point. So what I'm going to do is rewrite this. I'm going to do it as 2 separate integrals. I'll do the integral from negative 4 to 0, and then I'll do another one from 0 to 4. And I have an additional problem in that you're like, oh, okay, that's fine, but how am I supposed to find the derivative of this with an absolute value in it? Right? So I need to rewrite my curve piecewise. So if x is less than 0, so ignore everything else, just look at the absolute value, what do I have to do to the x to get the absolute value?
Multiply by -1.
That's exactly right. You got to multiply it by -1. So that's going to be x squared plus 4x minus x. That's going to be x squared plus 3x for x less than 0 or equal to. That works. And this function is smooth, right? And so I'm okay with that. And then if x is positive, I just drop the absolute value. So it's going to be x squared minus 5x for x greater than or equal to 0. And again, that's a smooth curve. So I'll just do this as 2 parts. Before I do that, I'm going to go ahead and find y prime. Y prime is going to be 2x plus 3 for x less than 0. I cannot include 0 there for y prime because this has a definite doink right there in the middle of the graph, right? So y prime doesn't exist there. And this would be 2x minus 5 for x greater than 0. So we'll do the integral from -4 to 0 of the square root of 1 plus the quantity 2x plus 3 squared dx plus the integral from 0 to 4 of the square root of 1 plus the quantity 2x minus 5 quantity squared dx. Jake, were you putting that into your calculator or were you doing something else?
No, it's something else.
Okay. I was hoping you had that done for me already. So let's quit out of this. Math 9, the integral from -4 to 0 of the square root of 1 plus the quantity 2x plus 3 squared dx plus the integral from 0 to 4 of the square root of 1 plus the quantity 2x minus 5 squared with respect to x. And it's 19.556. Okay. I do want to go back to this previous one. I wanted to make sure we had time and talk about, let's look at what would have happened if we had tried to do this in terms of x. Okay. So if we had tried to, and you don't need to write any of this down, but we would have said that the length was the integral from -8 to 8 of the square root of 1 plus 1/3 x to the -2/3 squared dx. What if we had tried to do that? So if we try to put that into the calculator, I'm not entirely positive, but I think it explodes. So we'll do math 9, the integral from -8, oops, not 5, 8 to 8 of the square root of 1 plus 1/3 x. Oh, need to insert a parenthesis there. Now I'll just redo it. 1/3 x raised to the -2/3 all squared dx. It immediately gives me an error message. You're like, well, what if I tried to break it into two integrals and went from -8 to 0? Right? Maybe that would fix the problem. Well, since the problem is at 0, I think it's still going to not be happy with this. La 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 la. The worst thing that happens when this happens on your calculator is you leave it, and you're like, okay, I'm going to go on to something else and come back to it. And you come back to it 5 minutes later and it's either still blinking or it blinked for 5 minutes and then it says, yeah, I can't do that. I'm not sure which is worse. Do you guys know now, because this does happen, how to get your calculator to stop when it's doing something like this? Because if you just press enter, it just ignores it. You got to press on, and that gets it to quit. I'm surprised you guys have never come across one like that where something went badly wrong and it just sat there forever. You've never done that to your calculator accidentally?
I think it's happened before, but I just
Turned it off and turned it back on. Yep. All right. Any questions? Okay, then tomorrow, if memory serves, we have a quiz. What will that quiz be on? Volume. Interesting that we didn't have, the other part of this was, areas in the plane and stuff. Well, that doesn't appear to be on that quiz. I wonder if we were supposed to have another quiz earlier and I just missed it.